My name is David McKay. This is an introduction to time series. Hopefully you're all at the correct session, and we're going to get started just now. So, I'm from Scotland. I work for a company called Influx Data. Our core product is InfluxDB, and it is a time series database. So, we're going to start with a small introduction, and before we dive into what time series data is, I like to do something. Oh, come on, clicker. There we go. We're going to do a quick pop quiz. I like history, so I'm going to make this a little bit about the history of time series and some surrounding concepts. I'll just give up on the clicker and use this. So encoding is something that we're all relatively familiar with as developers. We use encoding for many things. But encoding isn't a new concept. In fact, it was first used in 410 BC. It was documented by a historian, even for ancient Rome, where he talks about this person, a captain of a ship, whose name was Alcibiades. And what was interesting about Alcibiades was he was a hired gun when there was a naval war. So he didn't fight for any one particular side. What used to happen was he would show up, he'd take a look at the two armies that were fighting, and decide which one he was going to help. He did this through raising a flag to indicate he was going to fight for this side, and then they would all attack. Encoding was very simple back then. In fact, there were only one or two flag systems until the 14th century. So if you think about that, that's a lot of years before anything changed or progressed from the one or two flag system. It wasn't until the 15th century that things actually got a little bit more sophisticated. We had 15 flags, so were a combination of colors and letters and so forth. And this is actually still the system that is used today by ships and admirals. Something else, as developers, we have to understand, especially with distributed workloads like databases, sharding. Now, sharding, we may think, of course, is not anything the ancient Romans did here with regards to sharding, but they actually did. So sharding actually goes back to 150 BC as well, although it wasn't documented until many years later. But what they actually did was the ancient Romans had to send messages in order to win wars. In fact, the only way that you could win a war thousands of years ago was how quickly you could get messages to your troops and have them move around and change your tactics and so forth. And this is what they did. They split the alphabet into 5 different tablets. Each tablet had 5 different had 5 letters of the Roman alphabet on it. And then they would have a system like this, where on the left, they would indicate which shard or which tablet to use. So here it's the second. And then on the other side, they would actually indicate which letter on that tablet that you were used to send a message. And in fact, it was much more sophisticated than even that. Some of the modern day encryption things that we have actually were invented in ancient Rome too. We have like the Rot 13, the Caesar ciphers. These all go back to very, very old times. If you like history as much as I do, you may be interested in this book. It's called The Early History of Data Networks. Some of the references here came from this book, and it is packed full of random bits of knowledge that are really cool if that's interesting to you. OK, so what about the history of time series? We've talked about encoding, we've talked about sharding, but what about time series as a concept? Well, the ancient Romans did that too. Right? Time series is not as modern as we like to think about it. The ancient Romans have actually done everything. Here's a bit of text here. But essentially, the ancient Romans had the concept of investing in public companies and sharing the profits. Those shares in the public companies were traded among other people and sold. And this, although there's no written evidence that suggests the ancient Romans had time series data, you couldn't actually do this without having time series data. Someone had to be keeping a track of how much worth or how much profit companies were making in order to be able to sell those shares for profits and sell them to other people and so forth. So time series data goes back just as long as these other two concepts. A little bit more facts here is that the first IPO came from the Netherlands in 1602. The first IPO in the US was many years later. And then the first actual reference to time series as a term actually dates back to 1884. And this is when the first paper was published that tried to build correlations between the import price of wheat The export price of wheat based on the import price of other things, other textiles, silk, cotton, and so forth. So people knew there were correlations between how much money was available within the country to put the price on the wheat, and that was always affected by the imports from other countries and so forth. And that was the first documented time series that I could find, at least. Now, what's the point of all this is that we're talking about time series, so it's nice to get a little bit of history. But this was also the first paper that applied the dimension of time to statistical analysis, which I think is really, really interesting. In fact, here's a quote from the CTO at my company that says, most data is actually best understood on a dimension of time. So what we're going to cover today will hopefully teach you how to take advantage of these benefits as well. All right, finally, the introduction to time series. So what we're going to cover, we're going to talk about what is time series data. I'm going to break it down so it's quite understandable. We're going to have a quick introduction to why you should use a TSDB and not any other general purpose database for time series data. Because I work for Influx Data, of course, I'm going to be using examples from InfluxDB. But what I want you to take away from this is that everything just about I cover is very agnostic and does apply to every other TSDB as well. So. We're going to kind of touch on the value of time series data too. And when I talk about the value, I'm also talking about the cost of storing time series data. And storing time series data can get very expensive. We'll dive into some examples. I'm going to throw some big numbers at you and hopefully give you an understanding of what you're actually getting yourself into when you start to store time series data for longer. And then the last bit is a brief introduction into what you can do with your time series data to actually improve your monitoring. Lots of companies now are doing microservice migrations where we're taking the complexity of monolithic applications and pushing them down to the network layer or the operational layer. And to do that, monitoring has to change in advance. So what is time series data? Well, that's really simple. Any piece of data with a timestamp is time series data. That is the only requirement, right? So if you can see a timestamp, you should be thinking, hey, this is time series. So what we have here, and hopefully that's large enough for you all to read. But what I'm going to call events, things that could happen within any developer's infrastructure. So we have things like the memory usage being 100%. We have a health check failing, database migration runs, and a few other things. What's important here is that the bits that are highlighted in orange, these are things that would actually be a cause of concern. Right? When I see memory 100%, or a health check failing, or pods being killed by the OM, those are things that I consider relatively dangerous. What we have in a lighter orange is what we could consider causal events. These are not dangerous on their own, but they could have a knock-on effect or a cascading that could cause the more dangerous events. So running a database migration is actually quite a scary thing. Pods restarting can have unexpected side effects. Deploying a new version of your software, right, that's always dangerous. So we have causal events that affect the danger events. What we have in purple are events that should be, well, they shouldn't really mean anything, right? If a git commit has any sort of dangerous effect on your infrastructure, unlikely. CPU usage being at 12%, is that a cause for concern? Hopefully not. And then the red herring, the pink one, Scotland qualifying for a World Cup, that's never going to happen. So. Now, those events don't make much sense when I show you to them in that position. But if we apply the dimension of time, we actually start to understand what's going on here with these events. Right? We know that the memory consumption had 100%. The pod got killed. We were using the latest tag, so we've automatically got a deployment which we didn't want. That's triggered a database migration to run. Now our health check is failing, and we're stuck in a crash loop back off. Right? So this dimension of time is how we actually build understanding and knowledge of what is going on inside of our infrastructure. OK, so what is time series data? We're going to break it down into two categories. First, we have regular time series data. This is metrics. The only thing that makes something regular means that it's available on any certain interval. So if you want to fetch metrics every 10 seconds, if they're ever not available, then you then have irregular time series, which is the other category. So for the rest of this talk, I'm going to be calling this metrics and events. And events are unpredictable, so I do not know when the next one is going to happen. So when you start to do statistical analysis of time series data, you have to be able to identify which type of time series you're working with. Regular metrics are the ones that are probably more familiar to you. Right? If we're monitoring our CPU usage, we would hope that value is always available. Actually be able to go to the kernel and say, hi, what's the CPU usage? Memory usage is just the same. If I want to, every 10 seconds, ping Google to get a response, that is regular time series, and so forth. Irregular time series or events are things that we cannot predict. We cannot tell you when the user is going to click a button. We could forecast it, but we'll get into that later. You don't know when the next authentication request is going to fail. You don't know when the next CI job is going to trigger, and so forth. So this should be a screen that everyone is mostly familiar with, right? We've all got log data on our applications. And log data is time series data. At the start of every log line in your application, there is generally always a timestamp. Now, the logs are unpredictable, so we consider this irregular time series or events. And this is a football game. And the reason, that's a few blank faces, like what's going on here, is there's actually quite a lot of time series that we deal with in our daily lives, right? How many people are in the stadium is a metric, right? Maybe 50,000, 40,000, etc. We actually have events, irregular time series, so we can look at when the goals are scored and who scored them, right? We don't know, we can't predict when the next goal is going to be scored. If we could, we'd all make a lot of money. We have aggregations, which is a special form of a metric. So we have the score over 2 potential games, and so forth. So there's time series data everywhere. So how do we collect all this time series data and store it inside of our TSDB? I'm going to talk about Prometheus and Telegraph. Telegraph is a product that's also from Influx Data. Everything is open source. Prometheus exporters are, of course, very popular as well. So these all provide different methods. And I can honestly say I don't think I've ever found an occurrence where there's not been a Telegraph plugin or a Prometheus exporter that can fetch the data that I'm interested in. So they are pretty all-inclusive, and hopefully any of the inputs that you're working with here are the same stack that you're working with in your day-to-day job. The reason I'm listing the outputs here, this is a Telegraph-specific thing, is that Telegraph doesn't actually care if you're using InfluxDB. So you can still use Telegraph and write your metrics to Prometheus or to any other time series database. We support, I think, over 50 output plugins. And then we always get down to this debate about, well, should I pull my time series data or should I push it? And the question is, you actually need both, right? Pulling time series data works for regular metrics, regular time series and metrics, because it's always available. So I just pick my scrape interval and off I go. You cannot do that for irregular time series or events. So you really need to push them. And that generally means you have to instrument your code. So use cases for time series data. As developers, we're very familiar with infrastructure monitoring, application monitoring, and of course, monitoring SLAs on third-party service providers. IoT is a huge user of time series data. Every device that you have, smart devices, these are emitting many, many metrics, generally at sub-second resolution. And of course, real-time analytics. Every time someone browses to your website, you probably have Google Analytics or something else. Again, this is all time series data. All right, the database bit. So time series databases are purpose-built to handle this sharding of data over time. Right? That's why they're so good at doing this, and this is why you should be using one. Some of the key characteristics of a TSDB is you generally have to do very high write throughput, so the database has to be able to handle that, and I'm talking hundreds of thousands of points per second or more. Reads are very, very specific in a time series database, right? You would never go to a TSDB and say, show me all the values for this metric across all time, right? That would be a very painful experience. Generally, when we query time series data, we've got a very specific window in our minds or in our systems that we want to look at. So reads have to be built to handle that use case. So sharding on time is why that is important. When we talk about the value of time series data, that's when I'm talking about the TTLs or lifecycle management. Time series data is generally not something you want to keep around forever, and we'll get onto that in a little bit. This graph is from DBEngines.com, and it's actually tracking the popularity of databases over time. Excuse me. And the fastest growing category for the last 3 years has been time series data. So more and more people are now adopting TSDBs. The reason I think this is the fastest growing category is because of this microservice and cloud native kind of evolution that's happening with our software. Like I said, we're taking complexity from monolithic applications and pushing it down the stack. That means our networking stack and our operations, Kubernetes, is all really, these are painful systems that we have to adopt, but they make some parts of our lives easier while making other parts difficult, and the difficult parts are what need monitoring. So there was a study done by the New Stack, and they asked people, do you have time series data, and what do you store it in? 12% were using a TSDB for their time series data. So 88% of these people are using general purpose databases. Now, I think, other than this just being a cool picture, I think there's a reason why that number is low, and I don't think it's because people aren't using TSDBs, although I'm sure loads of people are using general purpose. But I think there's an offset, and it's that people don't always realize they're using a TSDB. So if your company has lots of money, then you're probably using New Relic. That is a time series database. If your company has slightly less money, you're probably using Datadog, also a time series database. Right. So I'm not sure how high that 12% would go if we told people these were TSDBs up front, but I reckon probably in the 20 to 30% range. And that's just a made-up number in my head. All right. Show of hands, who is running Kubernetes? Right. Every time I ask that question, more and more hands go up, so that's great. I done a Twitter poll. I think this was around a year ago. February last year, so yeah, a year ago. I had 1,000 people respond to this, and the question was simple. I run Kubernetes in production, and I monitor it with. Now, Prometheus is a CNCF project along with Kubernetes, so I expected that to be really high, and that showed. I think what was really surprising here was that 13% used nothing. Right. So everyone put their hand up to running Kubernetes. Who's running it without monitoring? Or who would feel comfortable without monitoring on Kubernetes? Okay. We can have a chat later. That must give you a little bit of fear, right? Kubernetes is a very complicated system is emitting thousands of metrics. It's probably not the thing you'd want to go unmonitored. Anyway. OK, so it's not too late. This is where InfluxDB comes in with a cape. It saves the day. Everyone's like, cool, I need to get me one of them. So the disclaimer is this is agnostic. I am going to use some InfluxDB terms. What I will do is try and use Prometheus terms as well as we go so that you can kind of build a correlation there too. OK, so InfluxDB introductions. It's a time series database. It's open source. We consider it a full stack monitoring solution in that we provide dashboarding capabilities. We do real-time streaming of the metrics, so you can build pipelines, serverless functions on top of it. And we have version 2, which has just hit beta phase as of about a week ago, maybe 2 weeks ago now. So when we talk about time series data, we're talking about points. Right? At any given point in time, the value of this metric was what? So let's look at an example here. If we're doing system monitoring, then we're probably going to be monitoring the load average of that machine. Here, we can see that a series is a combination of a metric name or measurement name, which is load, and the tag set. That is labels for the Prometheus people. Those provide a combination that we call a series, and that is a series of points. The fields are the bit in blue. InfluxDB allows you to have multiple fields on any given series, and the timestamp is a bit on the end. So whenever we talk about a point, we're talking about the series key, any sort of number of fields, and the time at which that point it happened or was scraped or collected. Now, to make the series thing a bit more understandable, if we think about the stock market as the best example I can generally come up with, right? If you want to monitor all of the companies and the NASDAQ or something like that, I think there's 3,000 of them, and you want to pull up the market, the ticker for Apple or Google, then that is a tag set with the measurement name, and that is a series. So any given ticker would be a series. Now, when we're talking about InfluxDB, when we talk about tags, we're talking about things that are indexed so that we can query our data and filter on those tags. It keeps it nice and fast. The limitation there is we only index strings, so your tag values can only be strings. Fields, on the other hand, can actually have multiple data types, and that's because they're not indexed. So you can be integers, they can be booleans, etc. They can even be objects. Now, the value of time series data is where things get a little bit murky, I guess, at best. So what I actually want to talk about when I say the value of time series data is that first we have to understand what are the costs. And that comes down to resolution, right? When I talk about resolution, I'm saying how often are you going to scrape this metric? So if you're a Prometheus user, you may be used to the 10-second interval. That is a 10-second resolution. The more frequent that is scraped, if we drop that to 1-second resolution, then that means we're going to have 10 times as many points as the 10-second resolution. And you can see how the growth of those metrics is going to be quite vast. So the value of time series is actually the resolution and how long we want to store it. Gives us the cost of storing that data, but then we have to think about the value. How useful is it for you to store time series data for more than an hour, for more than a day, for more than a month? And how do we adapt that resolution based on that value? Now that's not very specific yet, but let's try and break into that a little bit. Okay, so the cost of time series data is definitely not free. Let's go back to the load example, the load average example. So let's assume we're all familiar with this, hopefully. We're going to monitor the CPU usage on a machine and some other system metrics. So if I have one measurement, let's just say we want to monitor the memory consumption. I have one series, which means I have one machine, at 1-second resolution. I have 86,400 points per day. That's how many points, right? Now, what you have to remember here is that these numbers are actually going to be much higher than this, because generally we'd have more than one machine. So what if we add a second machine? We now have 2 series, gives us 172,800 points. Now, as we go run through these numbers, think about storing these as records in MySQL, Postgres, or any other general purpose database, and then try and work out at what point you get uncomfortable. OK, so now we're doing full system monitoring. So we've got 5 measurements. That means we're monitoring the CPU, the memory, maybe just some network stats, and so forward. We have 10 machines, which I'm going to say is quite a small number of machines for any modern production infrastructure. At 1-second resolution, right, numbers getting quite big now. If we wanted to monitor the NASDAQ, real time series use case here, there are 3,300 companies there. So let's assume it's just one measurement, the value of the tickers. And because this is financial data, the resolution is actually going to be millisecond or sub-millisecond, right? InfluxDB supports nanoseconds, right? I don't even know how big that number is. I've never worked it out, but we're in the billions per day, right? That's the bit you need to remember. This is not how many points I need for life. This is every single day. Who would want to store that number of records on a general purpose database? Right? That's quite scary. OK, so if we change the resolution from 1 millisecond to 1 minute, the number gets a lot smaller, right? We can see how we have to make some compromises when we're storing time series data. If we drop that resolution to 1 hour, we're back into very comfortable territory regardless of database. And then if we do 6-hour resolution, this is child's play. Anybody, you could store this in a CSV and you'd probably still be happy. So what this is a concept that's very specific to time series databases. They're not available in general purpose databases, and that's the concept of downsampling or roll-ups of data. And the easier your TSDB makes this for you, the more comfortable you're going to be at storing data at higher resolution, because you know you can do automatic downsampling as you go. With InfluxDB, this is version 1. I won't talk about the one in beta. We have a concept called a continuous query that monitors your time series data. You get to specify the window. Here, what I'm saying is I want you to roll up the data into hourly buckets. So store it at 1 millisecond, and then every week go through. Anything that's older than a week, roll that up to a 1-hour average, and that drops the number of data points down significantly. So roll-ups and downsampling, very, very important for TSDBs. Now, if you're storing events in your TSDB, you cannot take advantage of continuous queries because it's irregular, right? How do you calculate that average for something that's irregular? Well, you can't. What I would suggest is we have loads of articles on doing anomaly detection and outlier detection with InfluxDB, so you can just go and Google for that. OK, so now that we're storing time series data, we've got our downsampling in place, we're doing automatic rollups, etc. What does this mean for actually monitoring of our infrastructure? So let's go back to the good old days. Applications were very, very simple 10, 15 years ago. We had one application, ran on a server, we had one database, it spoke to that database, and that was it. Now, monitoring a system like this is not difficult. we've got very good at it. We say the CPU usage got a little bit high, reboot the machine. The memory consumption went a little bit high, just reboot the machine. If response times on our application get too high, just reboot the machine, right? Nice and simple. The Black Friday stuff was seasonal. We could do predictive load, and what happens if you worked in e-commerce in the late 90s is that whenever Black Friday was coming around or any other holiday period, you would run out and buy a whole bunch of new machines and set them up, and then go back and sell them again a week later. OK, now, why is this important? Well, because we have a very simple to fix, or we have a very simple to identify thing here. Is when do we know to page an SRE or an operations person because there's a problem? And generally, we just added health checks. Right? So we add a /health to our application. Whenever that stops responding, you generally send a page, and that was it. But then we started to scale things horizontally, and then this becomes a more difficult problem. Is that how do we send a page here? Well, we had to adapt. We couldn't just have a single health check. We had to have a health check on all of them. And that did some fixing. But really what we wanted to know is, even if we lose a node, is our application still serving good traffic to the people that want to see it? So then what you start to do is, OK, let's monitor for all the 500s. And if we get above 10% over a 5-minute window, maybe something's went wrong. And then we can go and speak to the operations team, and they can hopefully go and fix it. Oh, there we go. Let's look at the modern day situation here. Right? We're not just working with a single application that speaks to a single database. Right? We kind of shot ourselves in the foot a little bit. We're now doing microservices. So we've got service A, B, and C. Service C is doing canary deployments because we want to be able to test changes over a small portion of our traffic. The network is virtualized or defined as software. We have service meshes because that's a great idea. We then have multiple databases. Generally, every microservice has its own database. Where do you even begin to monitor a microservice architecture? Right. Things are very, very difficult. So I like to call this a kind of convenience versus cost. What we used to do with our monitoring was very symptom-based. If something went wrong, we looked at the symptom, and generally we just rebooted the machine, or we bought a bigger machine, and so forth. And you can kind of treat all of those symptoms for a while, but eventually you're going to have to solve the root cause. Right? And time series data actually gives you the insights into how your application is performing to work out what those root causes are. So you have to kind of upgrade your monitoring. The problem with that is the cost element. So you have to understand the more time series data I have, the higher I'm going to have to spend to store that data, but I'm going to get more insights out of it. And the number that people always throw around is take your cloud bill, work out 10%, and that should be what you're spending on your monitoring. I would say it probably should be a little bit higher, but your mileage may vary. And I like to think about this as causality. Time series allows us to understand the causality within our infrastructure and work out problems. OK, so how do we work out what went wrong in a system? Well, for a start, we need to have old data. So we have to look at the data from last week. We have to look at the data from last month. And if you have cyclic data or seasonal data, then it actually benefits you to store your time series data for years, so that you can do trend analysis over the last 5 years, 10 years, and so forth. So you have to kind of shape your data in a way that you can store it and use the rollups to take advantage of that. And because you're using a TSDB, we actually have a wealth of statistical functions that are available at your fingertips. Both Prometheus and InfluxDB offer just about every function, I think, on this list. So we can do linear prediction, right? Do I have in fact, there's an example in a minute, so I won't go into that one. But we can use hot winters. Let's talk about that. That allows us to look for seasonality in our data, spot trends, and then do predictions and forecasting based on that data. So if I do have an e-commerce store, and it's very busy every February, then I can start to look at the forecast for how much infrastructure I'm going to need in advance, instead of just putting my finger in there and guessing. OK, so I used to be an SRE. I'm going to share a small story with you, right? Has anyone here ever been paged at 4 a.m.? All right, not a few of you. I was a terrible SRE. Let's caveat that first. I mean, I was good at some stuff, but I hated. I'm not a morning person, and I definitely do not like being woken up at 4 a.m. So what would I do when a page goes off at 4 a.m. and it tells me that the disk usage on a machine is above 85%? Well, because I'm a terrible SRE that doesn't like being woken up, I would log onto the machine, I would do rm minus rf, I would delete everything in var log, var temp, I would start deleting any cache files that I could find, and I'd go back to my bed quite happy with myself that I fixed the issue, right? Obviously, I'm definitely treating symptoms here, and I'm not working out the root cause. What is generating so much data on that machine, and how do I fix it longer term? So really, I was shooting myself in the foot. But what if we have time series data of metrics here? We can actually use linear prediction algorithms to monitor the disk as it's filling up, predict when it's going to go above a certain threshold, and then tell me during working hours. What happens if I get that page at 3 p.m. on a Tuesday afternoon? I'm probably going to spend a bit more time on it and fix it properly. So linear prediction is just one of the applications of statistical functions that allows us to then not be woken up at 4 a.m. because we can predict it in advance. Another really good statistical function that's available in InfluxDB is mode. This allows us to actually introspect the time series data and find highly recurring values across our index tags. So we can say, oh, a particular user type, the request latency for page users is very highly, is 95% of the time, above 500 milliseconds, and why is that? And when we can identify frequently or highly recurring values, we can try to work out other correlations. So why is the page users get longer latency than the free users? Oh, because we do different ad tracking on the front end, and it's actually injecting artificial latency on all the HTTP requests. Right? We can discover these things a lot quicker by using the time series data. So that's just one application of mode. And of course, proactive operations, we do spend a lot of money on our cloud infrastructure or even bare metal data centers, right? If you can actually use Holt Winters and do predictions to understand what your, how many requests or users you're going to have to deal with next year based on the growth of the website over the last 5 years, then you don't have to over-provision by 50% or more to just make sure that you can survive those 2 days of Black Friday hell. So, just having all of this data available, getting statistical and understanding the data is actually going to give you a lot of value for your buck as well. And of course, once we have all this time series data, we can use that to power automations. So, using the historical data, doing predictions, tying that into ML frameworks, and FluxDB has really good support from a company called LoudML. That allows us to actually take all of the streaming data from InfluxDB, we can actually put it onto Kafka, we can put it through TensorFlow, and we can open up data scientists to our data and let them actually find out things we had no idea existed before. So, in summary, I'm hoping you all understand why you need to use a TSDB and not a general purpose database. Please do not use a TSDB and then not take advantage of downsampling and rollups. It's really nice to have real-time live metrics at 1 millisecond resolution, but don't store it for any longer than you have to. So identify your use case for the time series data and use the automatic rollup functionality. Make sure you understand the risk and cost of storing this much data. Build that into your system. Always do outlier detection on your events. You'd be surprised just how many interesting things you can discover about your application by putting your log data into a TSDB and using the mode function on it. And then build as much dashboarding as you can. Now, my caveat on dashboarding is it's great, right? Your manager loves having that dashboard and the 70-inch screen in your office, but there's no need to really have it on display. They're more of a debugging tool. Please don't sit there and looking at it all the time. So thank you very much. I hope that was a pleasant and gentle introduction to time series data. I'm happy to take any questions if there are any, and I'll be around today and tomorrow. I'm not shy. Just come up and talk to me, and I'd love to hear what you're doing and help you out. So thank you very much. Does anyone have any questions?
Just to understand the rollup feature, I mean, why do you use it exactly? Is it to free space, for example? I mean, say we have a full week at 1 millisecond resolution, and basically, if I understand correctly, all those values, you average them for 1 hour, 1 hour, 1 hour, and then basically, if I understand correctly, you delete all the 1 millisecond resolution points. Is this correct?
Yes, so you don't have to calculate an average. You can use any of the statistical functions. You could actually sum them, count them, whatever you want. You control that, but yes, you would say after an hour, I don't need 1 millisecond resolution. I can drop it to 1 second. Use the average, it deletes all the old points, and you have new records for that time window. And then after you've done the roll up to 1 second, maybe after a week you want 1 hour, and then after a month you want 6 hours. So you build all of that into your pipeline.
Okay, sure. Cheers.
Right, thank you. Any more questions? All right, thanks again.